So we're gonna talk today again about substitution and elimination, and you've already seen some substitution when we started talking about the different reaction types. And so with substitution, let me open up with that. Let's see. So when you have a substitution, you already kind of have an idea of what that is. So let me give you an example. Let's say Br plus, I'll say sodium. So if I have something like this, right, where I have a nucleophile, substitution is always going to involve a nucleophile and an electrophile. And then in my electrophile, we talked about this already, you have a leaving group, right? And so with that being said, what happens is in this substitution, I'm just going to put the arrows in right quick. Oxygen is going to attack here, and then you lose your leaving group. Let me fix that arrow. Right, so you end up with Na plus Br minus plus right, this molecule where the leaving group and nucleophile have swapped places. All right. So when you do a substitution like this, right, we're going to talk about two different pathways for substitution. It can be direct, like it is here, or concerted. Right? Or it can be stepwise. Right? This is not an example of a stepwise substitution, but I have several examples that we're going to look at. All right, so it can be concerted or stepwise. Same thing with elimination. Let me show you an example of an elimination. So I'm going to take the same molecule and I'm going to treat it in this case with a base. Let's do, I'll just do sodium hydroxide. Right? And so when you have a alkyl halide like this, right, there's there's two hydrogens adjacent to where that leaving group, on the carbon adjacent to where that leaving group is. Right, so when in an elimination, this is going to come here, boom, like this. And then I'm going to take those electrons and give them here, and then I'm going to force that leaving group out. Right? And then when I do that, I get water plus Na plus Br minus plus an alkene. Right? If you notice in the elimination again, one of the characteristics of elimination is the formation of a pi bond. Right? Every elimination results in the formation of a pi bond. Right? Anytime you do an elimination, you're going to get a pi bond. All right. So with that being said, let's jump in and look at these different types of elimination. So let me say this about elimination too. It can be also concerted or stepwise. It can be concerted or stepwise, just like substitution. All right, so let's jump in. And here I'm just going to show the two substitution types first. So substitution, so you have, and this is a long handout. I think I abbreviated it for this class. I also teach this in part 2 as well. So I'm not going to go into as much detail as I did with part 2. But we're going to just learn the basics of substitution and elimination. All right, so there are 2 types of substitution that we're going to discuss. One of them is SN2, the other one is SN1. And what we're going to learn from each of these discussions is we're going to learn I'm going to write it up here. The rate law, how to write the rate law. We're going to talk about the conditions of the reaction, because each substitution happens under different types of conditions, right? So we're going to talk about the conditions. We're going to talk about any requirements for the reaction, like for elimination, depending on what type it is, you need a base for one type, and for the other type, you don't need a base. So we're going to talk about that, and we're going to talk about how to predict the products. All right. So not in this particular order, but these are the things that we're going to learn from each of these scenarios. So we're going to first talk about the SN2. Let me put something else on here too. We'll talk about the transition states too. All right, and so for the SN2, this is, the S is for substitution. The N is for nucleophilic. And then the 2 is for bimolecular. All right, it's bimolecular. So substitution, nucleophilic, bimolecular. So in every substitution, you're going to have a nucleophile and an electrophile, right? So up here where it says label nucleophile or base, we're going to do that. Once we do that, we'll find what the substrate is and the leaving group. So let's do that first. Which one of these two in this very first reaction do you think is the nucleophile?
The SCH3.
Good, good. This is your nucleophile. You know that because it has lone pairs, it has a negative charge, and nucleophiles are electron pair donors, right? Lewis bases. So that's your nucleophile. By default, this becomes what?
Yeah.
Electrophile. Where's the reactive site in that electrophile?
The carbon attached to bromine.
Good, you're right. So this is my reactive site. Right? Excuse me, which makes bromine my leaving group. Right? In a substitution, it's important to identify that leaving group because that's what's going to get replaced by your incoming nucleophile. All right. So when that happens, what I'm left with is, and we're going to go through the mechanism too, because there's something about the mechanism that we need to know. So I'm going to show you it's on the next page. Right. So I should get a product that looks like this. Right. Plus Br minus. Right. So that's an example of what we call a SN2, right? The reason is the bimolecular part, the reason why it's bimolecular is because it is concerted. So we call the electrophile the substrate. Right, so that's my substrate. That's the place where the reaction is going to happen. And so what we mean by concerted is that the nucleophile is coming in and the leaving group is leaving, and it's all happening at the same time. So this is coming here, and then this is coming here. Right? The thing about the SN2 is that the nucleophile is always going to come from the opposite side of where your leaving group is. Right? Always comes opposite of the leaving group. But always attacks opposite of the leaving group, right? But it's happening at the same time. So let me show you on the next page, right here, right? So if this is my substrate, right? And this is my nucleophile. The nucleophile comes in from the backside of where the leaving group is. They never attack on the same side, but it's all happening at the same time, right? So because the nucleophile is coming in and the leaving group is leaving, that's why simultaneously, that's why we say that it's concerted. So you have simultaneous attack and leaving. So this is what the transition state looks like for any SN2 reaction. Nucleophile comes in, leaving group is leaving. You have a partially formed bond between the nucleophile and the substrate. Let me change colors right quick. And you have a partially broken bond here. Right, partially formed bond between the nucleophile and the substrate. and a partially broken bond between the substrate and the leaving group. All right, ask this question again. I'm gonna keep asking it. Is the, excuse me, is the transition state real or theoretical?
It's theoretical, isn't it?
It is. It's not real. So what does that mean? It means I can't isolate it. Is that right?
Yeah.
But what can I isolate relative to the transition state? There's
The
another
intermediate.
species. Speak up.
The intermediate.
Intermediate. Good. So with this concerted mechanism, there's no intermediate, right? You go straight from reactants to products. Are y'all following that?
Yes, sir.
And so so you go from reactants to transition state to products. And it can be endothermic or exothermic. I mean, it just depends on what bonds you're breaking and what bonds you're making. All right. So this is why it's bimolecular, because the nucleophile and the substrate are involved in the rate determining step. All right. So nucleophile is involved, the substrate is involved. So when we look at the energy diagram for SN2, which I also have over here, it looks like that, right? Where you have a nucleophile plus a substrate here. And then as time passes and those two things start to interact and start colliding and sharing electrons, you're moving up this hump right here, or moving up this diagram, right? Until you get to the transition state where you got partially broken and partially formed bonds, right? And then after that, you get to the products, which is here, right? All right, so knowing that the nucleophile and nucleophile electron are both involved in the rate determining step, all right, you can write the rate law. So for SN2, I'm gonna write it up here in the corner. So the rate is K, which is the rate constant. Let's a lowercase k times the concentration of the nucleophile, nucleophile, and then the substrate. All right, that's the rate law. And the reason it's written that way is because both the nucleophile and the substrate are involved in the rate determining step. All right. And overall, the rate is second order. Do y'all remember how we determine the order of reaction? It's just the exponents outside of the concentration, the terms here for concentration. Sorry about that. So there's a 1 outside of each one of those brackets, right? An exponent of 1. So it's second order overall. All right. Any questions about that? About the example or the rate law, or why we say it's second order, why we say it's concerted, anything? Add in a page here. All right. Let's look at the second example. I'm gonna copy it and put it on a new page because I want to show you something on that. Hopefully it copied properly. And it didn't. Let's see if I can get it better this time. All right, that's better. All right, so first of all, let's go through, figure out what the nucleophile is, what the electrophile is. And after that, we're gonna go back and I wanna show you this whole idea about the nucleophile coming in from opposite of the leaving group. So where's the nucleophile in this case?
CH3.
Is this, right? The negatively charged carbon. Right, so that's my nucleophile. And then by default, this becomes my electrophile, and then iodine is my leaving group. So what would the product look like from this substitution?
Instead of a I on that first, it'll be a CH3, and then the I will be by itself.
All right. You're right. So that CH3 is here plus I minus. All right. So so that's my product. And then if I think about how it happened, that carbon is attacking here. And I'm losing my leaving group. And keep in mind, this already has 3 lone pairs around it. All right. So carbon attacks the electrophilic site here. Uh-oh, not there. Or there. Here. Right. And then I lose my leaving group. Right. So the idea about this thing happening, the nucleophile coming from the opposite side of the leaving group, I'm going to draw this out. I'm going to try to draw it out in 3D. So here is the carbon. Here's my leaving group. And that carbon, I'm just going to draw I think it's 4 carbons. 1, 2, 3, 4, yeah. Right? So if I looked at, and I wish I had my model set, this would be a lot easier to show you. But if I look at that carbon from underneath, it kind of looks like this, where and I'm drawing this as a tetrahedral. You know that if you remember from CHEM, right? You have a tetrahedral has geometry that looks kind of like this, right? Where you have a group that's vertical, you have another group that's here, that's at an angle, bond angle of 109.5. Everything is 109.5, right? And then on the wedge, that means that this group, I'm going to put a here, A, B, C, and D. A is coming out of the page. That's what that wedge means. When you see it on the bold line like that, it means it's coming out of the page. And then D is on a dash line, so it's going back into the page or back into the screen, right? So if I take that and rotate it around, I can rotate it so that I can look underneath it, right? And so that's what we have here. So the nucleophile, the CH3, I'm gonna change the color of it. has a lone pair of electrons and is negative. So this is coming from here, right? And then by the same token, the bond between carbon and iodine, I'm breaking that. So I'm going to show that like this. Partially broken, right? And so whenever the nucleophile comes in, this is how it attacks. It's always going to come from the opposite side of where your leaving group is. So this is my leaving group. This is my nucleophile. And it always attacks opposite of where your leaving group is, right? And I could have shown the same thing on the ring, but I think it'll be, this is a little bit easier to visualize. All right, any questions about the SN2 or about this reaction right here? One of the things with SN2 that I'm gonna put up, make sure when we work examples, I'm gonna pull an example to kind of make the point. But it happens with what we call inversion, right? You always see inversion because of the way that the nucleophile attacks. Just keep that in mind, that it happens with inversion, all right? And I'll show you what that means. We'll talk more about it when we get to an example where I can point it out. One of the other things to point out about the SN2 is the solvent. Did anybody eat ramen last night? Be honest. Turn your camera on. Be embarrassed. All right. If you cooking ramen, and my kids eat it. My daughter loves those little 2-cent noodles. You got to do what you got to do. But one of the things about ramen, I don't know if you've ever done this, but I had a cousin staying with me one time, and she was a nurse. She worked late one night, came home, put some what's the one? Soba, I think, yaki something, whatever it is, Manchurian, the ones with the little cup, the cup. She put that in the microwave. She just hit start, went upstairs, came back, the whole kitchen was smoked up. The reason was because she didn't put any water in there, right? So she basically blew my microwave up. And then about a couple of weeks later, my wife told her she got to go because that was bad. Anyway, in order to make ramen, you need a medium to cook the noodles in. So water is the medium. When you're running a reaction, you need a medium, right? So in rare cases, you do a reaction under what's called neat conditions, where there's no solvent. But most of the time, 99% of the time, when you do any reaction, you do it in a solvent, right? And so the solvent is basically like the water for your ramen, right? You have the water and you put the noodles in, you boil them, and then boom. All right. So the solvent is the medium for the reaction. It's where the reaction takes place, but it doesn't. Let me not say that. I don't want to say that in general terms because sometimes the solvent can get involved, but it doesn't react, right? It may get involved through what's called solvation or something like that, but it doesn't react, right? So these solvents, acetone and dichloromethane, DCM, let me write that out too. So you'll know what that means when you see it again. So acetone, dichloromethane, those solvents are what we call aprotic. I need room. I'll put it right here. called aprotic solvents. Right? That word it sounds a little bit complicated, but it's actually not. What it means literally is no H plus. It cannot donate H plus, right? So acetone is aprotic. I have a list in this package too. DCM is aprotic. Let me see if I can find it. Here it is right here. So here are your this list, and this is on Blackboard, by the way. These are what you call polar aprotic solvents. So acetone, ethyl acetate, acetonitrile, DMF, DCM, and then THF. If you see any of these solvents, they're going to facilitate SN2 reactions, right? So the reactions, the examples we did up top, you had acetone and you had dichloromethane. Both of those are aprotic. There's a reason why you do SN2 reactions in aprotic solvents, right? There's a reason why that happens. Let me explain it. So let's say I'm just going to put a generic example down here. Let's say I'm doing a reaction with methyl iodide. So I'm going to do CH3I plus SCH3 minus, right? And I'm going to show this. So what would the result of that be? What's the nucleophile in that case?
The S.
Good, sulfur, right? And then that makes iodine my leaving group. It makes the whole thing my electrophile, and then carbon is the reactive site. So in the product, I'm going to get CH3, S, plus I minus. Is that right? All right, so that's my product. If you did, so does this fall into the category of a SN2?
Yes.
Yeah, if you just look at it. All right, I'm gonna explain one other thing about the SN2 also to make this make more sense, right? So when you look at this, this is your nucleophile. All right, with the nucleophile being negative, if you were to run this reaction in, let's say, water, let's not do water, let's say methanol. Because all your alcohols are what we call protic, right? If I run this in a solvent that's not aprotic, what happens is my sulfur nucleophile will get surrounded by protons. So all of these hydrogens here, here, this is in methanol, right? When those protons with those partially positive charges on hydrogen get around that nucleophile, it's a wrap. The nucleophile basically gets lazy, it relaxes, and is not as reactive, right? So this is why you have to do a SN2 reaction in an aprotic solvent, because a protic solvent will what's called solvation. It'll solvate your nucleophile. right? They'll do what's called solvation. So anytime you do a SN2, you want to do it in an aprotic solvent so that your nucleophile doesn't get hindered from reacting, right? Because when that nucleophile gets solvated, what happens is, but at the same time, the rate is going to decrease. All right, so that solvation is bad, right? It decreases the rate of the reaction. That's why for SN2, when you see those reactions done through a SN2 mechanism, more than likely you're gonna see them done in an aprotic solvent, right? So aprotic means no protons. It cannot donate H+, right? Protic, on the other hand, right, can donate H+. So protic solvents are more acidic, right? Because that's what it means when you have a H+ to donate, right? It means you are acidic, like a Bronsted acid type solvent. So water, any alcohol, any carboxylic acid, excuse me, is going to be considered protic, right? And then you have some other non-carboxylic acids, right? Like sulfuric acid, phosphoric acid, HCl, any type of acid is going to be considered a protic solvent, right? And so for SN2, you do not want to use protic solvents. You always want to use aprotic solvents. All right. Any questions about anything so far? All right. So we go back up to here. You can see again, both of these reactions are done in aprotic solvents. My suggestion would be just to commit them to memory, right? But an easy way to remember it is that aprotic solvent is not acidic. So it cannot give up H+. So anything that's not water, alcohol, or acid, we'll consider it aprotic. All right, any questions? All right,
No, sir.
all right. So let's jump down to SN1. The SN1 is going to be, it's still a substitution, but it's a little bit different from the SN2, all right? Well, actually, it's a lot different. It's a totally different mechanism. And one of the things I forgot to point out for SN2 is it's listed right here, though, that is favored on primary and secondary carbon. You see how we can't get away from that? But it'll never happen on a tertiary. So let me put that up here. Right, it'll never happen on a tertiary, ever, because if you look at what I showed down here, how the nucleophile comes in, a tertiary carbon is just too bulky for this mechanism to happen, right? So it can happen on a primary, it can happen on a secondary, but it cannot happen on a tertiary, because the nucleophile, the path of the nucleophile is going to be blocked. All right. So now let's look at the SN1, and let's look at a couple things about it. First of all, the S is for what?
Substitution.
Substitution. What's the N for?
Nucleophilic.
Nucleophilic. And then the 1 is
Unimolecular.
Unimolecular, good. Right, it's unimolecular. What that means, simple. The rate is only dependent on the substrate, not the nucleophile. So the rate is independent of the nucleophile. I don't care how good the nucleophile is either. It doesn't matter. It does not change the rate. The only thing that can change the rate of a reaction, of an SM1 reaction, is two things that can increase the rate. The leaving group, like the quality of your leaving group, or the stability of your intermediate. Those are the only two things that change the rate of an SN2. Right, so this is so the rate, let me see if I can got room to write that. So the rate is enhanced. My brain is working, my hand is working faster than my brain by leaving group and stability. Of an intermediate. Right? Those two things increase the rate. So first let's go through, and this is, again, it can happen on secondary and tertiary carbons. There's a reason for that. What do we know about tertiary carbons as it relates to making them positive? Carbocations. What do we know about that? Is that good, or tertiary carbocations good or bad?
Good.
They're good. It's the best one of the best carbocations that you can make, right? So with the SN1 and the way it happens, which I'm gonna show you in a second, right? A tertiary carbocation is a good thing. So let me just cut this one out right here. And let me cut this. And then that way we can go through the mechanism. I need all that. Technology, man. It seems like on Fridays, technology just doesn't want to cooperate. Let's see how much room we got on this page. Oh, plenty. All right. So this is, let me move this and put a, so this is gonna be an example of an SN1, right? Here's your nucleophile. Over here is your substrate. And then bromine is your leaving group, right? This reaction is different. It's not concerted. It's actually stepwise, right? And the first thing that happens is what? Somebody tell me.
The leaving group leaves first.
Loss of leaving group, right? Good. Somebody was been watching some YouTube, all right? So the first step in the mechanism is loss of leaving group, right? When that happens, you get a carbocation intermediate. Right? This is the rate determining step for this reaction. Right? That's the step that's gonna determine how fast or how slow the reaction goes. Right? So the rate determining step is always in a mechanism, that's always your slow step. Right? So you get this carbocation, is this tertiary carbocation. And then your nucleophile, which is in this case OCH3 minus, is going to come in and attack that. That step does not affect the rate. Right, that step has no bearing on the rate. So it doesn't matter how good the nucleophile is. It doesn't matter if it's in a protic solvent. The protic solvent can solvate the nucleophile all at once, right? It doesn't matter because the rate is determined in the first step, loss of the leaving group, right? And so the leaving group, if it's better or worse, that's going to affect the rate. Also, the carbocation that you make is going to affect the rate. This is very important that this is a highly stable carbocation. Right, that carbocation stability is that's going to be important to the overall rate of reaction. If you're making a less stable carbocation, then the rate is not going to be as, it's not going to, the reaction is not going to happen as fast. The rate is going to be a little slower because it's not, it's going to, the substrate is going to be less apt to lose that leaving group, right? So with the SN1, right, notice again, it's happening at a tertiary carbon, right? And I'm doing this in a protic solvent. Right? All alcohols are protic solvents. Right? Any alcohol is going to be protic. What the solvent does here is it actually helps the leaving group. It helps stabilize the leaving group because it'll solvate that leaving group once it leaves, right? Or even while it's leaving, the solvent can solvate that leaving group and help to stabilize it. Right? Let me see if I can fit that in somewhere. I'll just write it down. I'll write it right here. It solvate the leaving group and that adds stability. And it doesn't matter if it solvates the nucleophile too, because the rate is not determined by the attack of the nucleophile. Excuse me, is determined by the loss of your leaving group. All right. So when we think about the attack of the nucleophile, in this case, it doesn't matter, right? It's not, it doesn't have to come from the opposite side or whatever, because the leaving group is already gone by the time the nucleophile attacks. All right. I always use an analogy. Some people got one, a professor got mad at me one time when I used the analogy of like the SN2 is kind of like, how do I want to put this? Well, the analogy I use, like SN2 is like the one person is coming over while the other person is leaving, right? So one person going out the front door and then the other person is coming through the back door. Y'all will catch that later. And then the SN1 is different, right? The leaving group leaves, and so now the carbocation is free to date whoever it wants to date. So then that's when the nucleophile can come in. It ain't no sneaky stuff going on. All right. So with that being said, and knowing that this is stepwise, let me go back up to here. Actually, down here. Right. This is what the rate, the reaction energy diagram would look like. Right. So the first step is loss of leaving group, which is highlighted here. And then you get your intermediate carbocation, which you can't isolate. That's the difference in an intermediate and a transition state, is that you can isolate the intermediate. You cannot isolate a transition state. So that you get the intermediate, and then you go from intermediate to product. right? So the rate law for this is just K times the concentration of the substrate, right? The nucleophile is not involved. So this is a first order, right? Because there's a 1 here. It's a first order reaction, and it's only dependent on the substrate. And that matters, right? Because with the SN2, if I change anything about the concentration of the substrate or the nucleophile, the whole rate changes. Here, I can dump in 10 gallons of nucleophile and the rate won't change. All right, so we're gonna stop here. And does anybody have any questions?
Yes, I was just actually wondering where that sheet on the aprotic and protic, you know what I'm talking about, that you showed us earlier. You said it was on Blackboard, but I couldn't find it under assignments.
Really? Let me see right quick, because I might have given y'all a truncated version. So let me double check and let me share my screen back. Get to that class. Yeah, if it's not there, I can upload it. And plus, when I upload the notes, it'll be in there too. So we're in third module. Yeah, it's right here, I think. The overview, I think, yeah. Put that page, okay. I'll upload the solvent page and this other page with the energy diagrams. I will add that to this handout. And I think I want to add one other page, the page with the leaving groups on it. So let me do that, and then I'll swap that out, and I'll put it up in a few minutes.
Thank you.
I appreciate you pointing that out. All right. I got a meeting right now. So who was that asked me to do the extra credit, to show the extra credit?
I think it was Ms. Miller.
Oh yeah. Okay. What I'll do, I'll post it. I'll post the when I post the notes, I'll post a copy of the that part of the homework.
Okay, thank you.
Yeah, and then if you have questions about it, you could just email me.
Email you.
Yeah, because I got 2 meetings at noon. Okay, I see it, Kayla. Yeah, I got 2 meetings that starting at the same time, so I got to start one, so I won't be extra late to the other. So,
That's fine. It's no rush. I know it's extra credit. I just wanted to see if I did
check your answers.